So 6, we use 6 to 6.
Yeah, I wouldn't mind it. Let's get it up over there. Okay, so we just look at page 9 at the top. So we actually, everyone understood how the dipole forces work, and we looked at a positive pole and a negative pole, right? There are more examples of covalent compounds, and they are given there, right? So one very common one is the water molecule. And usually this comes on the exam, so please highlight this one here, right? This one here comes on the exam. It's a water molecule for the test, right? NH3. Just one NH3. You need to draw this. Right?
Draw what?
You're not paying attention now.
You draw what?
Yeah.
The same one. Draw that out.
Yeah, so similar things can come out. So NH3 and stuff. Pay attention to that. Yeah.
We're still on page 9.
Yeah, we're still on page 9. So let's look at the first one here. We got, we know the compound, it looks normal here, right? H2O. So when you read this compound here, it's telling you obviously there's 2 hydrogens and 1 oxygen. Now, in the periodic table, where is the H situated, on the left or right? So we got the H on the
Left. First one.
left, and then the oxygen.
Right.
So we got oxygen on the right. So when we look at these forces here, between them, do we have any, is it a dipole force here? Do we have a positive, in terms of electron negativity? Do we have an attraction in terms of electron negativity?
Yeah.
Yeah. So which one will be the
No positive one is
H.
right? And the negative, obviously.
Oh.
Right. Now, in terms of drawing this here, remember, we need to look at the valence electrons, right? So for H, right, we got 2H, right? And we've got, very dot here, and we've got oxygen. How many valence electrons? How many electrons around oxygen?
6.
And if we had to combine this here, right? Now we know we've got 2 H's there. So in terms of the combination of this here, we're gonna get one of the H's here, right? Combining here, and another one combining here. We're looking at the oxygen there. Yeah.
Before you move on like that, just can you just put me in the picture here? I'm a little bit lost here.
Yeah.
I'm looking at this H. You say it's plus because it's on the left, and you got your O, which is on the
Oh, this part here.
yes. Because now
This is in the
because
periodic table. We're looking
Yeah.
at over here.
because
Well-
when you're writing those symbols, when you're putting the H, you say H minus. So
Yeah.
now I'm confused now. So when you're writing it down, you say H minus, but now you're saying H plus. It's confusing me now.
Oh, maybe I said H minus, but I meant if this thing on the left hand side, it has a lower electron negativity because it's on the left. Because it's more positive, electronegativity is lower. So therefore, its force around, we said that this is the positive pole. You remember, like we said, like the world has a north pole and a south pole. Right? How do you work in terms of a positive pole and negative pole in a periodic table is all the elements that lie on the far left are positive and the ones on the far right are negative. Right? So if you're moving, that's why I drew this arrow. When you move from left to right, you move from positive to negative. So whichever one lies further to the left will be positive, and the one that lies on the right hand side will be negative. Do you understand? So
It's almost getting there.
yeah, it was from yesterday's explanation. We're just building up from yesterday's. If you look at the example there, in yesterday's explanation, we had A and B there, right? And then we look at HCl. If we look at the periodic table in terms of HCl, let's turn to the, I think there is one here on your...
Do we have copies for periodic table?
I'm going to give you all that, so I will give you all that. So I want you to turn to page 143.
I sent it on the group.
Which one? This here?
No, the periodic table.
Yeah.
it's in there.
Yeah. So let's turn to 143 on the text.
143.
Yeah.
Oh.
Right, so we're looking at 143, right? You're looking at the H there. You can see the H is on here. Can you see this, guys?
Yeah.
H is on the far right, right at the top.
Yeah.
And you're looking at the oxygen. It's moving. If you're looking at it, if an arrow is going this way, right? The electron negativity of oxygen is higher than hydrogen. So that, in other words, it is more on the negative side. On the negative, we'll say it's on the negative side of the pole, and the other is on the positive. So the poles always work like in this arrow direction. So if you're drawing the arrow direction, it will be always from positive to a negative, and it moves. Remember, the other way it works like this way. Here, positive to a negative. I did this yesterday, I'm sure. Yeah. So, in terms of writing compounds, we always write the one that is
From the positive
side to
and
the negative side. You get it?
That's why it's H2O.
So that's why we don't.
HCl.
That's why we don't write H2O as in. We know that H2O has one oxygen molecule and two hydrogen molecules.
Yeah.
But we don't write down O2H. The reason why we don't write that is because of the rules in the periodic table. We always write the one that is more positive first, and then the one that is negative after that. You get it now?
Okay.
Right? I'm just showing you how the direction works and how the compound is formed. Right? And thereafter we're looking at the bond in the compound. And the bond here is a sharing of electrons, which is a covalent bond. So we're just showing you the covalent bond. So like I said, in the tests and exams, you are required to draw a Lewis dot structure. Lewis dot structure means you're drawing these dots showing the valence electrons, and the X's also showing valence
So
electrons.
we're supposed to put the dots and X's.
Yeah, so basically, the reason why we use the dots and X, because if you have all dots now, it all looks the same. So for two different elements, we use a dot for one, and you can use an X for the other. Alright? So when we're looking at the bonds here, remember there's something, it has to satisfy the octet rule.
So it's
Right.
at the 8.
Yeah. So there must be, for the compound to be stable, or an element to be stable, it must satisfy the octet rule. In other words, it must have 8 electrons around it. So once it has 8 electrons around it, it can't attract any other element towards it. It can't do anything. It's a bond. Right?
There's a question.
Yeah.
The protons and electrons, they don't have to be the same number, right?
Protons and electrons are equal. The number of protons is equal.
Yeah,
to
but
the
now when it's
protons.
combined with something else, then that means you end up with the octet, then it won't be equal.
No, so don't worry. Protons
Yeah.
don't take part in bonding.
No, I'm just saying.
Yeah.
But you can end up with 8 outside.
Yeah.
And the number of protons inside will be less.
That's how it becomes positive and negative.
It's
because when it
yeah.
uses electrons,
Yeah.
it becomes
So,
positive because there's more protons.
the
than electrons.
protons
Yeah.
will be centralized. Let's say it's
And then you
like this here.
No,
Let's
I
say,
know that. I understand that. What I'm saying is, you can have, let's just say, oxygen, I've got 6
yeah.
inside.
So you'll have 6 protons on the
6
inside.
protons and then 6 electrons.
Yeah.
And then it combines with something else,
Yeah.
and it gets 8. Right.
You'll get 8 electrons, but the protons within also
Still
stay
same.
same. Yeah. The,
No,
number
I
of
was just
protons-
asking.
the protons don't take
Don't
part in
change,
the
yeah, don't
bonding.
change, no.
So because it's not taking part in the bonding, you're not gaining or losing protons.
No, I know that. I was
Yeah.
just trying to figure out how
No,
we
no,
manage the 8 thing.
I understand what you
Yeah.
saying. Yeah. So over here now, if we're looking at this bond, remember around this oxygen, we still have to draw the other. We've got 2 here, then we'll have another 2 here, another 2 here. 2, 4, 6, 8, and it satisfies the octet rule there. And then we've got a bond there. That bond then can be also shown by dash lines, right?
Yeah.
And they say, yeah. Yeah, so the bond can be shown by dash line. So you got the O here, and it can be done by showing a dash line. Dash line represents, yeah. Right, now let's look at the one in ammonia.
So both are correct.
What's that?
If you get
Yeah,
a question,
it depends, right? So if they ask you to draw the Lewis dot structure,
then it'll be that.
you're doing the dots, Lewis dot structure. If they're asking you for a condensed,
Lewis structure.
yeah,
Can you
yeah,
write
it's
that
called
down?
Lewis dot structure.
Can you write that just below? So I'll take a picture,
Lewis
you'll know.
dot.
Yeah, it's probably in the notes too.
That's what I remember.
No, so what happens here in the notes, guys? They're expecting you to know N3 chemistry. So that's why it's not giving you all the detail like the other subjects now. They're expecting you, it's building from N3 chemistry
Yeah.
this year. Alright, so that's why it's not there.
And this is called it?
No,
So if they don't ask for that, you can do this.
yeah, this here is called the, what's this? Condensed formula. It's called a condensed formula. Or dashed bond form. But I don't want to write that there, but yeah. This you just need to know. They won't ask you for this. Usually they ask you for the Lewis dot structure. Right? Then let's look at the next one. Okay, let's take it down quickly. I'm trying to use this one board because I was noticing in my videos that it was coming too small.
This one,
Yeah.
cut it out.
And these pens were. But when you watch it, it's not so bad. Yeah, you can see it right there. Right, everyone has it down?
Yeah, I posted it. Sorry.
Right? Let's go on to the next one. So the next one we're looking at an ammonia molecule. The ammonia molecule is given by the compound NH3. Ammonia is given by the compound NH3. Right? NH3 is made up of 3 hydrogens and 1 nitrogen. Now if we go to your periodic table and we look at nitrogen, what group is in nitrogen? Group? Let's look. Group 5. So how many electrons around the nitrogen? 5. Right, so
It's 8 minus 3.
yeah, so that would be the number of valence electrons. So the total number of electrons is 5, but the number of electrons for bonding is 3. So you know that nitrogen has 3 valence electrons. Valence electrons means that it can create 3 bonds.
Available for burning.
Yes. I did wrote that. I'm sure I wrote that down yesterday. But anyway, you're listening to it. The video is going to be posted, right? Yeah.
So it got 3 prostitutes.
Available for bonding. What's that mean?
The flap keeps dropping down.
Oh yeah.
And you can't move it, and it's sitting directly on you. So
And then you're listening.
I'm
Yeah.
getting sick.
What we need to do, I think we need to bring this desk a little bit more fun and slot another one. So make 2 rows of 3, and then one there you can sit underneath because it doesn't hit you, right?
Perfect.
Even
Yeah.
if it does,
You want to swap seats?
no.
Very
I like my space.
Alright, no, but I'll put this desk in. You will sort it out, right? So you won't. I guess even when I'm sitting here, I do feel it a bit.
It's continuously on you.
Yeah.
Yeah.
Alright, so let's look at the bonds there. Remember, there's 3 valence electrons there. There's 3 valence electrons coming from the 3 hydrogen. So we get 3 bonds being formed. This one you must know, I told you guys why. Remember? Right? This one, yeah. The triple one there. So it forms 3 bonds. Then we're looking at something CO2. The next one we're looking at is CO2, carbon dioxide. Right. And in carbon dioxide, you can see what we did here. We put the C as a central atom. We put the C as the central atom. Because remember, the carbon has, if you look at carbon, what group is it?
Carbon group 1, 2, group 4.
Right. And then 8 minus 4?
It's 4.
So how many bonds possibly you can form?
4.
Right. So if we look at there, we're looking at oxygen, which is 8 minus 6. That means each oxygen can form 2 bonds, and carbon can form 4 bonds. So basically, it created 2 double bonds. You get it? Created 2 double bonds. The covalent compounds discussed above exist in the form of discrete molecules with little force of attraction between the individual molecules. This is true of many covalent compounds and accounts of many of them being gases, volatile liquids, or easily fusible solids. There are some giant molecules or macro molecules. The word obviously macro means large. Macro means large, if you didn't know that. Macro means large. And obviously the opposite, micro means small, right? Okay, so we'll be going down there, we're saying that however, diamond and silicon dioxide, in which directional covalent bonds extend throughout the whole structures. You know, diamond, guys, is one of the hardest substances on the earth, right? And the bonds in diamond is just organic bonds. It's between carbon and hydrogen. You know, if you press coal over, I think it's like thousands of years, a coal will turn into diamond.
That's how you get
Yeah.
diamonds.
The diamond bond is just a
Pressure.
long chain hydrocarbon organic bond, and it has the same bonding.
Is hydrogen in there as well?
Sorry?
It's also got hydrogen as well.
Yeah. It's hydrogen. Diamonds contain carbon and hydrogen.
I thought it's just pure carbon.
No, it's carbon and hydrogen. Right? Basically, it comes from you know the coal? The coal has the same bonds as diamond, but diamonds have a longer chain. Right? It's a macro molecule. Okay, it's very hard to break because there's thousands of bonds in there. Right? You get plastics that have similar types of bond. High density polyethylene. HDPE and such. It's also regarded as a macromolecule, which is a long chain. Yeah. And then the other, you eat butter and margarine. Who prefers margarine?
Plastic.
Plastic.
Who eats butter? Butter.
Butter.
Right, so the reason, the difference between butter and margarine is, butter is like a natural organic compound. Margarine is also an organic compound, but it is processed and synthesized. So it's a long molecule. The difference between like what's this other PVC, right? Polyvinyl chloride and margarine is like about 10 bonds. That's how bad it is. So and then they make it seem good because they say they push omega-3. They put some good fats with this organic molecule, and they say, hey, it's got omega-3, it's gonna lower your cholesterol. But it's still bad for you. It's very bad. What happens pretty long, if you eat it like over like 40 years or so, you'll start to build plaque around your arteries. Yeah. And then like you only see it like if you like, let's say you start eating margarine as a child. By the time you're like 50 or something, 50 years into having something, it starts to build up. Yeah. And certain people are predisposed to it. If you don't do cardio and you're not active, then you just say, hey, it's bad news.
Yeah, some people put it on their bread as if they're putting cheese on.
Yeah. And then there's even with cheese, you get two types of cheese. You get natural cheese and processed cheese.
I don't like
all the processed stuff is your body doesn't digest it properly, and when your body doesn't digest it, it goes into your bloodstream, and it's like literally it's like plastic in your bloodstream. And then what happens? It gets caught here at your heart because your veins, it travels through your veins because these are quite thick, right? And then when it goes to your heart, around the heart, there are small arteries, and then it gets starts clogging up here. Yeah.
Cocaine.
It's a cocaine glass.
Yeah.
That's like diamond, but man-made, right?
Yeah. Cubic, that's why I told you that the cubic, it's just plastic. It's shiny plastic.
Is it?
Yeah.
It's not actually like.
It's not this thing. It's not diamond at all.
Look. Okay.
It's synthetic. That means we can make it in the lab. Diamond, we don't make it in a lab.
Yeah.
You can't. We can't make
have
diamond
synthetic
because
diamonds,
the molecules are so long that they can't. It takes the conditions to make it. So the other one, cubic, what? Zirconia.
Zirconia, yeah.
Yeah, those are synthetic. We make those. It's like plastic, and they use a special laser cutter to make it look smart, and then they use a polisher and they shine it up, and it looks like a diamond. You like will never say, unless you like you look in. How you look at it's a diamond. They use a magnifying glass, and then they shine light on it, and then there's this what a diamond does is it creates a spectrum. You see like a rainbow.
Yes, imperfection.
Yeah, so you see a rainbow. It takes white light and it breaks it into Roy G. Biv, red, orange, yellow, green, indigo. So you see that like slight rainbow in it when you're looking at it over light, and then you know it's a real diamond. Otherwise, you don't know the weights. No, they can even make the weight of those cubic zirconias heavy, so you think it's real.
Yeah.
You smash it with your hammer.
No, but there's a machine that they use that tests the hardness of it and tell.
Yeah. But you can make it quite tough, eh? They make those things quite tough. You can get expensive ones for up to like 10,000 rand, cubic zirconia. They put in, they call it this thing, the Swarovski crystals.
Yeah.
Yeah, those are junk. It's not this. You're paying like 5 grand. Hey, but it's not real, That thing doesn't appreciate in value. All the rare metals, your gold and your diamond, your platinum, it appreciates because those are precious metals. We can't make it.
Yeah.
But the other ones, hey. Right. But you mustn't tell your wife now. Alright, let's turn over to page 10. we're continuing with the covalent bonds. Okay, so let me see, read the last bit there. We're talking about the last paragraph. The nitrogen atom in the ammonia molecule contains 2 electrons not involved in the bonding, right? A lone pair of electrons, while a boron atom in the boron trichloride molecule is 2 electrons and a short stable octet. An example of this compound is disobeying the octet rule. The octet can be completed thus, looking at the following. Turn over, guys. So we got NH3 there, guys, right? And we got boron, it's BCl3. Now we got this 2, I think it's boron trichloride. So we got boron trichloride and ammonia combining together here. Right, now let's look at the free, the unpaired electrons. Tell me how many unpaired electrons in the ammonia. Look. Tell me. How many unpaired electrons in this ammonia? 3. 2, guys. Look, can you see the 2 X's there?
Yeah.
Can you see the 2 X's here?
Yeah.
There's no dots around it. Right? There's no dots around that. So it's 2 unpaired electrons. So how many bonds can be formed? We would say like how many bonds? Possibly 2 bonds. Now let's look at the boron trichloride. Right? Does it have any free electrons?
No.
No. Right, and around the nitrogen, how many electrons? 2, 4, 6, 8. So the ammonia is satisfied the octet rule. Right, let's look at the other one. The boron trichloride. Is it satisfying the octet rule?
No.
2, 4, 6. Right? So one satisfies the octet rule, right? The other one doesn't satisfy the octet rule. But if we put them together, what will happen? If we put them together, what happens there? They bond together, right? And then they satisfy the octet rule. So basically, there's a sharing of bonds between this ammonia and boron trichloride. Although the boron trichloride didn't have any free valence electrons. Can you see that?
Yeah.
So so sometimes there are exceptions where it can break the normal rules. And we said, remember what I told you initially? When something satisfies the octet rule, it can't bond to anything else. But there are rules, exceptions, like this here when ammonia will combine with this one. When it's combined, and when one compound that satisfies the octet rule and another compound that doesn't satisfy the octet rule, but still has space for electrons, then a bond can be formed. That's what in the previous paragraph, that's what I was reading and explaining there, right? Now let's look at it in terms of this thing. So a coordinate bond is represented by an arrow, right? Pointing the donor to the acceptor atom. You get that? Coordinate bond. So it's the arrow is pointing from the donor. So it goes from the donor to the acceptor. And this is called the coordinate bond. Right, so remember this ammonia donated its 2 electrons to this boron trichloride, right? And when it donated that there, if we go around the boron, you can see it satisfies the octet rule. You go around the nitrogen, it satisfies the octet rule. So in terms of the coordinate bond, to show the direction of the donor to the acceptor, we show an arrow. the arrow goes from the donor to the acceptor. Okay, you got it? Okay. Yeah, so a coordinate bond is represented by an arrow pointing from the donor to the acceptor, or by a single line with a negative charge on the acceptor atom. Right? So the other one, what we can do is, we can show a positive and a negative. That there also tells us, okay, that the bond, this one was the donor, and this one is the acceptor, but the positive and the negative. So in other words, positive, negative. Okay. Other example of compounds containing coordinate bonds are carbon monoxide, right? CO. Right? You all know what's carbon monoxide, right? Remember, we get CO2, CO3, CO2 and CO3. Remember, this is carbon monoxide. This is carbon dioxide. And this is carbon. Right, so mono means one, di means two, tri means three. Alright? So yeah, so we're just looking at the forms of carbon and oxygen there, right? In changing the oxygen, with single oxygen it's mono, two oxygen is di, three oxygen is tri. When we get to the organic chemistry section, we're going to go and learn this thing, IUPAC naming of compounds, of organic compounds, right? Remember that I told you about the International Union of Pure and Applied Chemistry? They come up with a set of standard rules. So someone in France speaking a different language, thinking different now, they'll still use the same rules to name compounds. Because what was happening in the past, early 1900s, somebody's finding an organic molecule, they're naming it after themselves. Like boron, found the element boron is 8, we call it boron. You know, like that. So they now put rules such that everyone can now, you don't have to have a memory to remember the names, because there was thousands of organic molecules and everyone's finding different organic molecules. What they said is, okay, we'll set a type of rules. If you know these rules, you can name any compound, right? For organic chemistry though. But in organic chemistry, it's like the old way. It's just random. There is rules, but a lot of the compounds have their own names. Like this here, NH3, ammonia, right? Or like H2O, water. You know, that name has got nothing to do with the actual compound. Right? It's just named by somebody, which makes it very difficult when you got thousands of compounds like water, ammonia, right? What's a thing you'll use for baking?
Baking soda.
Baking soda. Yeah. Bicarb. Yeah, bicarbonate soda. So that's the calling name. But what is the compound of bicarbonate soda? Right, homework.
Just sodium or something.
Yeah, that's your homework. Give me the compound for bicarb. Go home and you'll see it in the check. Yeah.
NaCO3. NaCO2.
NaCO2.
Sodium bicarbonate.
Sodium
Baking soda.
Bicarbonate.
Yeah. But why are you giving the answer? Killing my Alright. So yeah. The rest of you didn't hear him. I want you to look at it, right?
Yeah.
Alright, so yeah, we're looking at the compounds here, and we're looking at next at other examples of compounds containing coordinate bonds are carbon monoxide and nitric acid. Right? As you can see, the negative carbon and the positive oxygen. So what is it telling you there? Which one is donating and which one is accepting?
Which one?
For carbon monoxide, which one is the donor and which one is the acceptor?
Donor is oxygen.
Oxygen.
Right? Acceptor is
Carbon.
right. Well done. Now let's look at the next one there. We've got nitric acid, HNO3, right? HNO3 is nitric acid, and then now tell me which one is the donor and which one is the acceptor?
Donor is nitrogen. Acceptor is
Oxygen.
Right, I want you to write that down in your books. Write it down there. Write down the acceptor donor. So when you're learning later, we'll come back here. I know it's small, but yeah. But guys, everyone's okay? You understand? So the last one, we're looking at nitric acid, right? So basically I was asking, which one is donating its electrons to the bond? We said that the donor is always a positive one, and the acceptor is always the negative one. You see the arrow shows the direction of the donor to the acceptor. Can you see that? So nitrogen will be the donor, oxygen will be the acceptor. So the positive one is the donor, negative one is the Alright, so yeah, let's move on to the next example there. Next we're looking at something called ammonium chloride. It's an electrovalent compound. So it's no longer a covalent bond. Remember what is an electrovalent compound? The other day, on Saturday I spoke about
Transfer of electrons.
Right, transfer of electrons. It's no longer sharing, it's actually going to send one electron to the other side, right? So, let's look at this electrovalent compound, right? Ammonium chloride, right? So, which is the positive part? NH4 plus, right? And then remember when we said about electrovalent compounds, you'll always have a negative or positive, either element or compound attached to it. So which is the positive part? It's the NH4 plus, right? And the negative part is Cl minus, whose formation of ammonia and hydrogen chloride can be considered to involve the formation of coordinate bonds. Right, so let's look at it. So its initial state was NH3, they were taking ammonia and they're adding ammonia to HCl. So basically this is what was happening here. You got NH3, right, plus HCl, right, and it's yielding NH4 plus Cl. So if we look at it in this, don't worry about the notes for now. If we're looking at it like this here, we got NH3, HCl, and then we got NH4 and Cl. So what does it tell you? That this hydrogen went to
Jump ship.
yeah.
Right away.
Yeah. It got transferred over. Right? And then remember when something loses an electron, right, and something gains an electron, what happens? So this here, yeah, so we're looking at the charges. If we're looking at NH4,
if you lose it,
It gains, so it will be negative.
Minute minus.
yeah, no, but in this case,
You're positive.
If you lose it, minute minus.
oh, okay,
Gain
sorry.
positive if I lose.
Because this we're looking at it in the third state. Now this is after the. We're looking at this here is not the intermediate state. This is the final
Final
state.
state.
This is the final state. In the intermediate state, right, a compound is formed, right, between this, and this compound formed here, this compound formed here is NH4 plus and Cl minus. Right? And the complete loss or gain of electrons in electrovalency and the sharing of electrons covalency and dative covalency in order to attain a stable noble gas configuration are useful theories that are helpful in explaining the formation of bonds between metal and non-metal atoms, such as sodium chloride, and between many non-metallic atoms such as nitrogen and water. Right? Note that these theories cannot, however, account for the strong bonds that are formed between metal atoms. So these covalent and ionic bonds, we're looking at it, but it's not very strong bonds. There are stronger bonds between metal atoms. Right? You know when you have like alloys, you all know what's an alloy. Alloy.
It's metal.
Carbon, exactly. Right? You hear about it, say alloy wheels, right? The reason why we have alloy wheels is, remember, they're taking something that's strong and mixing it with another metal that's not strong. Okay? When we do this here, we mix the properties. Because one property might have stainless steel. Now imagine if your car rims weren't rust proof, right? And your car is going through water all the time. What will happen to the wheel? It starts rusting and it will fall away. Right? It will break easy. So they mix two types of metals to get the best properties to create an alloy. So we have a metal now that can be resistant to rust, right? But the reason why we make an alloy and not use just a normal metal, because it's too expensive to use a metal that's totally rust proof, or pure. Pure metals are precious because you have to mine those metals, right? And alloys, we take a pure metal and mix it with another metal to get an alloy. So alloys are a mixture of metals.
It's like downgrading.
No, but
Yeah.
that's not. Well, also certain properties like with your rooms, you want them lights are also flexible. They don't-
Yeah. So it's a number of properties that they look at the material. It depends on the type of alloy. Right? Remember, like your pans or the cookware you're using, you got different types of alloys there for different types of. Yeah. So Teflon, you know that what it does to a pan.
Non-stick.
It makes it non-stick, right?
Wow.
Yeah, it does rub off.
It rubs. You're eating pepper.
Yeah, that's the thing. Once your pan starts going, you mustn't use it anymore, because what happens? The small pieces of metal actually get into your food. You wouldn't notice it, but it does. The Teflon starts to get into your food once the pan is destroyed or it's scratched. So you must stop. That's why they start saying that you must use cast iron. So when you use cast iron cookware, the metal doesn't get into your food. Yeah, it's very expensive though.
And,
What's that
stainless
brand?
steel?
You see the orange and blue and
There it's that's something.
yeah, it's a French brand. Yeah. You know the one.
Ceramic coating.
It's titanium.
Yeah.
Titanium.
Wait.
I'm gonna
You
come.
can, but it's so expensive. Yeah.
But the stainless steel,
Huh?
stainless steel, like AMC.
Yeah, AMC pots. Yeah, AMC pots are gone.
Yeah, this the steel.
Yeah.
Same thing.
Yeah.
Cheap, but half the price.
You can get those other pots. The other pots don't last long. It just gets wrecked.
Stainless steel.
Stainless steel ones are good, yeah, but you get
What's stainless?
yeah, you get different grades of stainless steel.
18H.
Yeah.
Not the 18.
Okay, let's go into. So we're looking at these metals, right? And we're looking at the bonds between metals. X-ray analysis shows that the atoms of many metals tend to pack together as closely as possible. Now remember we looked at the we didn't look at the three phase of matter, but I put the video up there. for you all to look at. When you have a chance, you need to go through your chemistry videos, right? The three phases of matter, we look at the particles in the bonds. I spoke about it, I said, you know, when some things are closely packed, we know it's a solid, right? Now with metals, these things are tight, bro. It's very tight. Remember, how do we break bonds? Somebody said, you said it the last time. How do we break bonds? How do we break these bonds?
Apply heat.
Just apply heat.
That's about crack
Heat is a form of energy that can break bonds. But when you add heat to a metallic bond, it doesn't break as easily. You need to add high amounts of energy, so it means very hot, right? Very hot, right? So X-ray analysis shows the atoms of many metals tend to pack together as closely as possible in 3 dimensions, right? In much the same kind of way that marbles would arrange themselves if put into a box and shaken, right? These closely packed spheres in 2 dimensions is shown in figure 1.1, right? The physical picture of metallic structures accounts for quite adequately for 2 properties: its malleability and ductility. Right? Malleability, what does that mean?
Shaping.
Yeah,
Shaping.
so bending. And ductile?
Stretching.
Yeah.
Ability to stretch.
Alright? Since it's easy to visualize the atoms altering their positions as they had slipped over each other when subjected to stress or strain, it's assumed that each metal atom in the crystal pools its valence electrons, and that these free electrons cement the positive ions together. In respect is some resemblance between metallic bonding and electrovalency, as in shown in the diagrammatically in 2 dimensions in figure 1.2. Alright, obviously you can't see this. Yeah, I'm just going to show you. So we'll go to photograph that. Since we missed out time.
Oh, so far.
Oh. I want to put that for 5 to 3.
What you said you got 1 hour video?
Huh? No, I said we'll go to 4 o'clock since we missed out time. Huh? Why? All of you are going to cuss? You're not relying. Anyone relying on public transport here?
On a Friday.
Come Abby, have a heart.
Check out evil man.
As it is, the guys got so much of homework.
Watch,
Maths and physics. Looks like those two, they always collude with one another. They say, give these those. Like those two always collude with one another. Say, hey, give these those extra homework.
Yeah.
The party don't cheat. No one it is.
Oh, some better than mine.
What? Still searching YouTube for math help? Are the videos from 2006 really helping? Aren't you tired of finding...
In this video, we're going to take a look at metallic bonding, which is the type of bonding you get between metal atoms. And we'll see how this gives rise to the characteristic properties of metals. Then lastly, we'll consider how alloys differ from pure metals. To recap, we've already seen that metals bond to non-metals through ionic bonding, and that non-metals bond to other non-metals.
So we looked at this here already, right? This is the electrovalent bonding. Okay. And then we look at the non-metals and non-metals, which is covalent, right?
through covalent bonding. Now we turn to how metals bond to other metals, which we call metallic bonding. If we think of a solid metal, it basically consists of a giant structure of atoms that are arranged in a regular pattern. In this picture, we've shown each atom surrounded by the electrons in its outermost shell. When all these atoms are together in a metal,
you can see you're looking at the electron clouds here around each atom, right? And these are the small e's are the free electrons or valence electrons, right? That are now stuck together in terms of a metallic bond.
although they actually give up these outer shell electrons and share them with all the other atoms in the metal. This means that the atoms will all become positive ions because they've lost negative electrons. And because those electrons are now free to move about, we call them delocalized electrons. So there will now be loads of strong electrostatic attraction between the positive ions and the negative electrons. And it's these forces of attraction which hold everything together in a regular structure. So we call this metallic bonding. This gives the overall metal strength and means that most metallic structures have high melting boiling points, so are solid at room temperature. They are also good conductors of electricity and heat, because the delocalized electrons can carry electrical current and thermal energy throughout the structure. Another important property is that metals are malleable, which means that they can easily be bent or hammered into shapes, for example into thin sheets. This can be a bit confusing because we think of metals as being strong, and in many ways they are. But the fact that metals have such a regular structure means that the different layers can slide over one another. So they're not quite as fixed as you might have thought. At least that's the case for pure metals. If we want a harder metal that won't bend so easily, then we can make alloys, which contain two or more different elements. We make these either by mixing together two different metals, or sometimes a metal and a non-metal. And we generally pick elements that have different sized atoms. The reason that this helps is that the combination of different sized atoms disrupts the metal's regular structure, and means that the layers can no longer slide over one another, making the alloy much harder than pure metal. In our example,
yeah, so what it's saying here is that in normal metals, we have bonds, right, in terms of the electrons coming out, and then we have an electrostatic forces between these bonds, okay? Now with the alloy, when you put these over this metal over another metal, the bonds being formed can't create electrostatic forces, so it can't go over one another. So that's why it's actually a stronger force, because it's harder to break those bonds.
Here we've shown steel, which is made up mostly of iron, but also contains 1 to 2% carbon. It also sometimes contains chromium, manganese, or vanadium, depending on which properties.
So your steel, right? Your steel is an alloy, right? It contains mostly, I think it's like 80% iron, right? And then 1 or 2% carbon, chromium, manganese, vanadium.
We wanted to have. And this gives it the strength that it needs to be used in things like cars and planes. Anyway, that's all for today. So if you enjoyed it, then please do give us a like and subscribe.
Alright, so we'll stop over here. I will post some other videos. Before you guys go, start packing up, I want you, did you actually read any of this? You didn't have a chance to read any of it.
We didn't.
So what I want you guys to do is actually, I want you to go over these half reactions for me. Page 12, right? I want you to look at page 12, 13, up to 15. Right, we're going to look at the different energy forms when a bond creates, when the bonds are created, and we're looking at the different energy levels. Right? And then we're going to learn these different types of energies. Okay, so you can just read through it for now, And then when you guys come back on Thursday, we'll actually go through some examples. And so for this year, I'll put on the background videos of this year. I put on the background videos for the first lesson, but I don't think anyone watched it.
And we'll see you next time.
Sorry?
There's just too many videos.
Yeah, it was whenever you can, you're going to get time now. You're going to have a long break to next week, Thursday.
Yeah.
Right? And then those of you who are coming tomorrow, remember, have your questions already formed in your mind. And we want to be focused, right? So if it's something specific you don't understand, you come with a question, we'll work with you with that question. Right? If it's math, science, or whatever, right? Japanese will send out the schedule for the Saturday timetable, right? So just pay attention to the group. I don't know if it's already sent it.
No, that's it.
Okay. This is your assignment. I gave both in the first lesson. Yeah. Yeah, so I'll see you guys, some of you tomorrow. Remember, if you're coming tomorrow, personal message me, guys. Personal message me. Tell me what you're coming for and what sections you want to focus on. And then I can arrange it with the guys to speak about it, right? What's that? Thanks, Ellie. See you. See you this week, okay? Yeah, I'm okay. You just go well. You coming tomorrow?
Where's success?
Yeah.
Uregile.
Okay.
Awunalutho ozoyenza ekhaya.
Hey, you okay?
Awungakwethu noma uyona kuphela engishaya ukwazi ukubamba lokho kunye. Ungakwenza lokho uziphase informal ukuthi next trimester
Come on,
Ngayizolo wenze nje ngisiqophele ukukhothile kodwa akazi usulokukhona. Hayi nasakhona uzobuya imisela.